Hello, everybody. Hey, this is going to be a lecture on momentum, and this is during first period. So what you're going to do is going to make notes on this video and then submit it in there. And so I'll probably be talking to some of the students in here, but you'll see all of that information up there. All right, you guys. We are going to be talking about momentum. All right, so you guys, what is momentum? What is momentum? What would you say?
Like the energy that creates, like, forces an object to move.
The energy that forces an object to move. Okay, I like that. It's not quite right, but a lot of those elements are there. Doctor, how about you? What is momentum?
Something that has movement.
Okay, definitely movement. Okay, what else?
A force.
Okay, definitely related to force. Okay. Now, you guys have certainly heard of momentum before, right? But unlike some of the other comments that or terms that we've had before, even though everyone's heard it, it is kind of less understood from a normal day-to-day sort of thing. We use it a lot. We use it in a lot of times. We'll use it in a sports analogy when a team has momentum. How would you say, if you were going to describe momentum from a sports point of view, how would you describe that?
I'd say like in a sentence, I'd say like the red team has more momentum than the blue team just because they're winning by a lot.
Okay, so the red team might have more momentum because they're winning. How about you? How would you describe momentum? Any yellow spot? How would you describe momentum in terms of a sports sort of thing?
They have more I guess oomph to them.
Say that again.
Like more oomph and
more oomph.
More power.
I love the oomph part. Okay, and as we'll see, that even though it's kind of very simple, I think the oomph part is probably pretty good. As we'll talk about. Good morning. I'm recording this lecture, and you're gonna see it up there. You're just gonna take notes, so these notes are good. But the question is, what is momentum?
Like power.
Okay, power.
Like something that like makes an object.
Say that again.
Something that like kind of like makes an object move.
Something that kind of makes an object move. Okay, now you guys, we're going to kind of cover all that, but momentum is just mass times velocity. Okay, now you guys, the symbol for momentum is P. Okay, and that's just equal to mass times velocity. Okay, now with even though P is the symbol for that, I think when I have taught this as an introductory sort of thing, I just use MOM. So MOM being momentum, so that is equal to mass times velocity. And we'll see that that idea of the oomph is really kind of good. Okay, so now if we're going to compare, let's say two cars. We're going to take, let's say, an Austin Mini that's going 20 miles per hour versus, let's say, a big Ford F-150 pickup truck going 20 miles per hour. Which one has more momentum? Yeah.
Probably the bigger truck.
Probably the bigger truck. Why? Because there's a bigger mass. Okay, now, same comparison. If we've got that Ford F-150 going 5 miles per hour and we've got the Austin Mini going let's say 70 miles per hour, which one's going to have the more momentum? Well, it's a little bit harder to tell, right? But if we're comparing, even though we got a heavier truck versus a smaller car, the car is going so much faster that it probably has more momentum, right? So in order for it not to be greater, that means the truck would have to be 14 times greater in mass. Okay, so if we have some object like that Ford F-150 going, let's say 15 miles per hour, and the Austin Mini, let's say going 45 miles per hour, it would be kind of hard to tell because we don't know exactly what those masses and velocities are. In fact, they could be equal. Okay, so you guys, we're going to kind of go a roundabout way and talk about what we do know, what we have talked about, and how it is related to momentum. Okay, but I want to review a few things here, and we're going to get into that similar to the worksheets that we've been doing and the quiz 14.6. Okay, so let's review here because it came up. Energy. You guys, what is energy? What is energy? Eric, what is energy?
Something that has like power.
Kind of. Now, power, which I've heard you guys say a couple times, power is just how fast energy is used. And we haven't really talked about it from a formal sort of sense, but you guys have heard of power, but it's how fast you use energy. Okay. Now, and we've talked about energy before, and I think all of you know what energy is, even though it's still hard to define. Okay. And I'm going to say energy is okay, energy is the ability to do work. Energy is the ability to do work. So what does that mean? So I think when a few weeks back, Miss Wallace in her lecture on energy, it was the something along the lines of the ability to make a change to itself or the world around it, kind of that interaction. That's probably a little bit easier to understand than the ability to do work, because you guys, what is work? What is work? Now, you guys have obviously heard of work, but as in homework, or that you have a job and you have to go to work, obviously we're not talking about that. We're talking about from a physics point of view, okay? And work is force times distance. Work is equal to force times distance, okay? So for example, I've got this calculator, I'm going to apply a force and it's going to move, right? So if I apply that force over a greater distance, okay, I am doing more work. Or I apply a greater force, okay, it's going to do more work. And I think you can probably understand that. Now, if I apply that work upwards, okay, what am I working against? If I'm applying that upwards, that force and distance upwards, I'm working against gravity, right? Okay, now, if I apply that to something and make it go faster, I am working against inertia. So we could also say that work is also equal to the change the change in kinetic energy. So if we make something go faster, okay, that requires work. That requires work. So if I take something and throw it, obviously it started out at 0 and then it's going faster. So you guys, what is kinetic energy? What is kinetic energy?
Energy and motion.
Anything that's moving is kinetic, is going to have possess kinetic energy, right? Which is certainly a good understanding. What do you guys recall? What the equation for kinetic energy is? Yeah.
1/2 mass times velocity squared.
1/2 mass times velocity squared, 1/2 mv squared. Now, you guys, you don't have to memorize that, but you got to know where it is. So memorizing is probably a better idea. So obviously, if it's not moving, it doesn't have any energy. Okay, and let's talk about what is a force. What is a force? So think about explaining what a force is to a kindergartner. What is a force? Guy, what would you say a force is if you're talking to a little kid? Say that again?
When someone or something acts on you.
What does that mean, acts on you? I mean, what you're saying is right, but think about it in a more simpler term.
Like pushes or pulls.
I think that's like a simpler definition. Okay, so it is a push or pull. Okay. Now, obviously, that's not a mathematical thing as to what force is, but it's really kind of a good idea. Now, so we're going to say that force is equal to mass times acceleration. Force is equal to mass times acceleration, which is Newton's second law, if you remember back about Newton's second law. Now, you guys, if I push against this whiteboard, is the whiteboard accelerating? Obviously not, right? But that means that the whiteboard is pushing back. It's pushing back against me. So what we really want to say here is we're going to want to say the sum. Okay, so that symbol right there, the Greek letter sigma, means sum. So we're going to add them all together. Okay, so if we have two opposing forces that are equal, then obviously it's not going to accelerate. Okay, but I think we can think if we push something and it moves, it's going to accelerate. Okay, and that is a push. Okay. All right, so you guys, obviously this momentum, mass times velocity, is the only new thing we've talked about thus far. This is a lot of stuff that we've already talked about, okay? What we perhaps did not talk about was potential energy, okay? And potential energy, we can just think of as stored energy, and the only kind of potential energy that we've really talked about as far as calculations go would be gravitational potential energy, which is equal to mgh. All right, so now you guys, we're going to have another term, which is impulse. Now, you guys, we've obviously all heard of impulse, but not in terms of physics. We probably heard it in terms of like a psychological sort of thing. Why did you hit your little brother? Or why did you take a cookie that you shouldn't have? So obviously we know impulse in that regard, okay? But when it comes to physics, this impulse, and we're going to use I, is going to be equal to force times time. Force times time. Okay. Now, you guys, if we look down here, work is equal to force times distance. Work is equal to force times distance. So we can see that they're related. So if I take this calculator, right, and just imagine it's on a table, right? If I apply a force over a certain distance, okay, this is going to move, okay? And if I apply a force for a certain amount of time, it could move as well, right? So what's the relationship between work and impulse, okay, is the relationship that we have between all those kinematic terms going way back. So just, you don't have to write this down, but I'm just going to kind of remind you. We could have average velocity is equal to distance divided by time, which is equal to v final plus v initial over 2. That was one of our equations. V final is equal to v initial plus at. Distance is equal to VIT plus 1/2 AT squared, and V final squared is equal to V initial squared plus 2AD. So those were those 4 equations from way back. And we can see that we've got a distance here and a time here. We've got a distance here and a time here. So obviously, you guys are related. Think about distance and time being velocity. And if we look here, acceleration is the change in velocity over time. Okay, so what I'm going to do is I'm going to kind of erase this, except for the acceleration. So anyways, this is obviously in your notes, kind of way back from the beginning of the year, not to mention the beginning of this this quarter. Okay, so I want you to think about having this acceleration is equal to the change in velocity over time. All right, next new thing. Okay, the change in momentum. The change in momentum is equal to impulse. Okay, change in momentum is equal to impulse. All right, so the change in momentum is most likely mass times the change in velocity, right? So when things are moving, typically they are not going to lose mass or gain mass. We could construct an example where the mass is changing, like you're carrying a bag of sand and there's a hole in the bag, and as you walk, the mass is getting less. But typically it's going to be like this, okay? And now we're going to have our impulse is equal to force times time. Impulse is equal to force times time, okay? Change in momentum is equal to impulse. Now, what if we divided both sides? What if we divided both sides by time? On this right-hand side, okay, the t's would cancel out. And now we're going to have mass is times the change in velocity over time. Okay? But you guys, what is the change in velocity over time? And it's that's acceleration, right? So we could say that force is equal to mass times acceleration. Okay? So this force being equal to mass times acceleration is the same one that we have down here from Newton. So we can see that all of that stuff is related. Okay, so if it's all related, why does it matter? Why does it matter, and how come we need to talk about momentum when we've got all this other stuff that is related? And here is where we're going to review You guys, we're going to review on some stuff that was in quiz 14.6 stuff that we've been doing for like 3, maybe even 4 weeks. And that is going to be essentially an imaginary roller coaster. An imaginary roller coaster. Okay? So I am going to, I'm going to kind of get rid of this. And let's say that we're going to have something like this. We're going to have a ball up here. We're going to say H is equal to 2. We're going to say this mass is 1 kilogram. And we're going to say the initial velocity is 0. We're going to say H is equal to 0. H is equal to 0 down here at the bottom. Okay, so let's talk about mechanical energy, kinetic energy, gravitational potential energy, height, and velocity, right? So these are all the things that we've already talked about. So if we talk about the top, you guys, how much kinetic energy is there at the top of this thing right here?
0.
Why 0?
Because it's not moving.
It's not moving. Okay, so even though we know that kinetic energy is equal to 1/2 mv squared, we know it's not moving. So we know that there is 0 kinetic energy. Okay, how much gravitational potential energy is there? How much gravitational potential energy is there at the top?
20 joules.
What's that?
20 joules.
20 joules. Remember, gravitational potential energy is equal to mgh. Mass is 1, gravity's 10, height is 2. Okay, so we're going to end up with 20 joules. Okay, and we already know that this height is 2. What is the mechanical energy? What is the mechanical energy?
20 joules.
You guys, it's 20 joules because conservation of mechanical energy. You guys, the total energy is just all of the kinetic energy plus the potential energy. That's mechanical. So we know that this is 0, this is 20, so the total has to be 20. Okay? So if we're talking about the bottom now, how much mechanical energy do we have at the bottom?
20 joules.
20 joules. How much energy do we have anywhere along this path? 20 joules because energy is conserved. Now, when we talk about mechanical energy, when we talk about conservation of mechanical energy, we are certainly ignoring all the thermal friction side, right? So we're assuming that all this is is frictionless and all that sort of stuff. So just the idea of conservation of energy, ignoring friction, is mechanical energy, which is going to help us. All right, so at the bottom, how much gravitational potential energy do we have at the bottom?
0.
Why 0?
Because the height is 0.
Because the height is 0. So remember, gravitational potential energy, mgh, our h is 0. So there's no kinetic energy. Sorry, no gravitational potential energy. So what is our kinetic energy?
20 joules.
It's got to be 20 because it has to add up. 20 plus 0 is 20. 0 plus 20 is 20. So they've got to be the same. All right. Now, here is perhaps the trickier part. How fast, you guys, how fast is our object going at the bottom? Okay, so if we have this 1 kilogram object, now obviously if it's going down the hill, it's going to be moving. So how fast is it going? Now I'm going to remind you, and this is in your worksheets or whatever, but from kinetic energy, velocity is equal to the square root of 2 times the kinetic energy divided by the mass. You guys remember that? All right. So we're going to have, in this case, the square root of 2 times 20 divided by 1 kilogram. 2 times 20 is 40. So we have the square root. We have the square root of 40. Okay? You guys, what is the square root of 36? It's going to be 6. 6 times 6 is 36. We go backwards to square root. We've got 6. So it's obviously going to be more. It's going to be more than 6. You guys, what is the square root of 49? It's going to be 7. So it's obviously somewhere between 6 and 7. And as it turns out, when you put that into your calculator, your velocity is going to be about 6.3 meters per second, right? So 6.3 meters per second. All right. So this is where, you guys, this is where we're going to come back. We're going to come back to our ideas of momentum. We're going to come back to our idea of momentum. So let's say at the bottom, we have we've got another ball that has a mass of 1 kilogram. Okay. So when this purple ball comes down and it hits this ball, okay, what's going to happen? What's going to happen to the velocity of our purple ball? What's that?
It's going to decrease.
It's going to decrease. Have you guys ever played pool or billiards, right? You may have observed when you're playing billiards that when one ball hits another ball directly head on, okay, the first ball stops and the second ball continues, right? And it continues ideally with the same velocity, okay? That is called an elastic collision, and we'll talk more about collisions later. But what if we had this come down and this was a ball of clay and it rolled down and it hit this? What would you might imagine that would happen to the clay ball when it hit this ball? It would probably kind of deform a little bit, and they would continue there because there's going to be some of that. That is called an inelastic collision, which we will talk about later. But right now we're just going to talk about, think of these as billiard balls that just have a bigger mass. And this one's going to hit and stop. So what velocity would you suppose that this black ball at the bottom will obtain after the purple ball stops when it hits it? What would the velocity be? 6.3. Why would you say that?
Because ideally it would proceed with the same velocity that the purple ball was at.
What concept are you thinking of when you say that this one is going to be going 6.3?
Conservation.
What's that?
Conservation.
Conservation of energy. That's exactly right? Now, so think about that. You knew that intuitively without necessarily knowing that it was conservation of energy. When you thought just a second longer, you obviously came up with that, right? But conservation of energy would answer that question. Okay, so this would go from 6.3 to 0, and then this one would go from 0 to 6.3, right? So I want to point out that this right here has got the same, it's got the same mass. The same mass. Okay, now, you guys, what if this second ball now had a mass of 2 kilograms instead of 1 kilogram? What do you think? What do you think the velocity of the second ball would be after the first one hit it? Half the velocity. So we'll call it 3.15, something like that. Now, you guys, that right there is a very logical answer. And as we'll see in a second, it's not quite right, but that's kind of the logic that I want you guys to think about. Okay, you guys, what if this was now 20 kilograms? What would this velocity be? So instead of it being 3.15, now it's 10 times more massive. So now maybe it's only 0.3 meters per second. Okay, what if we made this 2 million kilograms, right? 2 gazillion, right? This essentially is going to become kind of like a wall, right? So if it's so massive, it's going to become like a wall. So if this purple ball came down the hill and it hit this wall, what would happen to the purple ball? It would bounce back, right? Okay, so and that's if it's an elastic collision. If it was a clay ball, it would probably just hit and stop, right? So what we have here in a collision is things are going to bounce off each other if they're elastic, right? So now if we kind of go back to this and we make this 2 kilograms, okay, so what's going to happen as this one comes down, it's going to bounce back a little bit. And then this one's going to go forward. So even though it's a very logical answer to that, this would be half the velocity, some of this is going to go back. Okay, now we're going to be able to answer. We're going to be able to answer exactly what those velocities are when we get into, there's going to be an equation that we're going to be able to calculate how fast they're going. Okay, and in which direction. Now, that's going to be, you guys, that's going to be a little bit tricky, and it's a kind of a more complicated equation, but if you just plug in the numbers, you'll kind of see what happens. All right, so here's the interesting part, okay, is if this one comes down, okay, this 2 kilogram object essentially should go back up so that the height is equal to 1 meter, right? So remember, there was 200 joules, there was 20 joules at the top. So we come down here, it hits, since this is twice the mass, okay, when it comes out here to 1 meter, okay, 1 times 2 times 10 would also be 20 meters. So this 2 kilograms would come up and it would reach 20 joules right there, okay? Now, what if we had, and I'm going to kind of make this a little bit longer. Okay, now, what if we had this purple one come down and we've got 1 kilogram, 1 kilogram, 1 kilogram, 1 kilogram, okay? So this one hits this one and they're all touching, right? Okay, what's going to happen there?
The one like furthest away is going to
This one's just going to go up with what velocity?
from the first one.
The same thing as 6.3, okay? Now, what this might remind you of is something, this physics toy called a Newton's cradle, okay? And if you have not seen this homework, there was like a 4-minute video that you're just going to watch, which is, think of all of these on strings, and they would then go back and forth, okay? They're going to go back and forth, okay? Now, what's interesting here is if we have one ball come down, we could have 2 balls. We could have 2 balls that came up, okay? And let's say they're 3.15 because we have 1 kilogram and 1 kilogram. Okay, you guys, these 2 balls coming up at half the velocity, okay, it technically wouldn't be half the velocity, but we could explain that by conservation of energy. We could explain that by conservation of energy. But we find when one ball comes down, it's always one ball that comes up. It's never one coming down and 2 going half as high. Or 1 coming down and 3 going up. It's always 1 to 1. And if you watch that video, if we had 2 came down, then 2 would go up. 3 came down, 3 would go up. It's very curious, and if you've seen the video, it's kind of entertaining as well. And what explains that is not conservation of energy, okay? But what does explain that is conservation of momentum. Conservation of momentum. So that is really, okay, there is a conservation of momentum. That means momentum is not lost or gained. It stays the same, okay? And that is really kind of curious, and we will see things that will come up when we talk about collisions, all right? So you guys, this was definitely kind of a long sort of thing, but I wanted you guys to see it in the beginning to think about, hey, it's not just energy that's conserved, but it's also momentum. And energy is a lot easier to see it being transferred. What's a lot harder to see is that momentum is conserved. Now, you guys, if we think about momentum being conserved, one good example would be two people on ice skates. Okay. All right. So if we had person A on ice skates and we have person 2 on ice skates, and they are going to, now they're going to push off each other, right? Okay, so if the initial velocity is equal to 0 and this initial velocity is equal to 0, how much momentum do they have in the beginning? Okay, remember, momentum is equal to mass times velocity. So you guys, how much momentum does each skater have? 0, because the velocity is 0. All right, now, what if they push off each other? Okay, if they push off each other, okay, then this one, let's say, goes 5 meters per second. Okay, if when they push off each other, this one goes 5 meters per second, then how fast is the purple one going to go if they have the same mass? Let's say they're going to have 50 kilograms and 50 kilograms. Okay, so the question is, in conservation of momentum, if they start out with 0 momentum, then how much are they going to have at the end? They start out with 0. It's not going to change. How much do they have at the end? It's going to be 0, right? If this one's going 5, 50 times 5, this is 250 kilogram meters per second. Okay. What does this one have to be going in order to make it add up to 0? Okay. And this is the one that's a little bit curious because it is, we got to deal with negative numbers. So this one is going to be negative 5 meters per second. And negative times 50 is negative 250. negative 250 plus positive 250 is going to add up to 0. Okay, so that's kind of that conservation of energy. All right, so you guys, there is, you guys, we're going to stop here and we'll talk about the next concept here in another video. Okay, all right, so we will see you guys on the next one.